Hi, I am Dion Fafrod from Rohde & Schwarz. I am pleased today, together with my colleagues, whom I will introduce shortly, to launch a new webinar series called Avionics Testing. The focus today, in the first webinar in this series, is on air navigation testing. Before going into details on today's webinar, allow me to provide you with an overview on some of the competencies that Rohde & Schwarz has in this field. The competencies listed on this slide range from avionics testing for flight navigation, as well as for technology-specific avionics systems, such as the aircraft radar, satellite, and communication systems. This includes onboard as well as ground-based and, of course, the satellite-based components of the respective avionics system. To be a bit more specific here, for aircraft radar, for example, this would include onboard radar warning receiver testing, active electronically scanned array radar or ISA radar testing. For satellite, today this includes applications such as high throughput satellite link testing in the Ku and Ka bands. However, in the area of aircraft communication, I may add, Rohde & Schwarz is not only a provider of test equipment, but also a provider of aircraft communication systems. And together with system integration partners, also an avionic test system provider. And this is both in the RF as well as in digital or time domain. As a market leader in EMI EMC testing, Rohde & Schwarz provides solutions that range from turnkey systems to specialized instruments, components, and software for compliance testing according to the civilian and military standards. More information on this and on the professional technology training will be provided in the wrap-up session. Besides the listed competencies, we currently also recognize and work closely with technology leaders on current aerospace market trends. One such trend, namely the evolution of unmanned aviation platforms, invites a wide variety of new aerospace business models for our customers, for our partners, and for Rohde & Schwarz. For example, as is shown in the photograph on this slide, a drone-based platform is being used to perform tests on a VHF omnidirectional range ground station, or VOR ground station as they are known, and the drone payload is in fact a Rohde & Schwarz signal level and modulation analyzer, whereas this Rohde & Schwarz test instrument is most typically deployed as an aircraft or onboard flight inspection analyzer, and now here, clearly also in a drone-based application for ground inspection testing, that is. Depicted on this picture is a simplistic representation of the urban air mobility platforms, or UAMs, that are currently being developed for future potential markets, such as air taxis, for example. In the evolution of these unmanned aviation platforms and business models, it is clear that the corresponding aviation standards and regulations still need to be defined. As such, Rohde & Schwarz is working closely with technology leaders and authorities in supporting the current evolution of test systems and standards across a broad variety of new avionic technology platforms, including also the hybrid electric aircraft propulsion application. With that brief introduction, allow me now to introduce you to today's webinar program. First of all, my colleague Klaus Theissen will provide you with an overview of the Rohde & Schwarz portfolio in the field of air navigation testing, including next-generation test solutions in the quest of enhancing aviation and aerospace safety, security, and cost optimization. That will be followed by a hands-on demo from my colleague Paul Denisowski, who will show you how you can accurately and easily simulate avionic navigation signals on a Rohde & Schwarz vector signal generator with various state-of-the-art air navigation test functionalities. Following these two presentations, I look forward to providing you with a wrap-up that includes an outlook of the further avionic test webinars that are being planned in this series. Without further ado, I'm pleased to hand over to my colleague Klaus Theissen.
Thank you, Deon. Let me briefly introduce myself. My name is Klaus Theissen and I work as a product manager at Rohde & Schwarz with particular focus on T&M devices for terrestrial navigation analysis, which is the main topic of our webinar and my presentation today. I shall provide you with an overview of various solutions that Rohde & Schwarz has in its basket. So in fact, and you will see that soon, it is more than only analyzers. In general, we can say that civil aviation and military operations depend on accurate distance, location, and direction measuring systems. Of course, all air navigation systems, such as landing systems or en route navigation systems, require precise tests and periodic verification. This is very important from a safety and security point of view, as system failures may place lives at risk. Rohde & Schwarz provides a wide range of test solutions for different technologies used in the air navigation world. These solutions cover every need from design, development, and production to operational maintenance. Terrestrial navigation systems are subject to regular inspection and maintenance in the field and in the lab. Rohde & Schwarz offers high-quality measurement solutions for different applications in different form factors, from portable, lightweight, weather-protected, battery power testers to high-precision lab instruments. Let's try to get a quick overview and look at the different solutions and applications. The first is field tests of terrestrial navigation signals. These tests require lightweight instruments offering fast and highly reproducible measurements. Secondly, we have classical signal analysis in the frequency and time domain for development and production, and also spectrum and antenna analysis with handhelds for a variety of applications in the field. Then we have, of course, generation of navigation and satellite signals plus power measurements needed for a lot of applications, such as power measurements on DME installations. Last not least, I would like to mention radio communication testers, as they are closely connected to the navigation solutions. On the next slides, I will go a bit more into detail. Looking at field tests for navigation signals, we find different analog or digital and continuous or pulsed air navigation signals to analyze. The first two instruments I would like to focus on are the EVSG 1000 and the EVSF 1000. Both instruments have absolute identical RF measurement and signal analysis capabilities, but as you will see, completely different housings, as they are designed for completely different applications. The EVSG is the instrument to be used if the measurements are done manually or with a measurement vehicle. The EVSF can be installed in flight inspection systems and can also be used aboard of drones. Both instruments allow the analysis of the instrument landing system ILS, the ground-based augmentation system GBus, the VHF omnidirectional radio range VOR, and marker beacon signals, whereas ILS, VOR, and marker beacon are the classical analog signals, and GBus is a D8 PSK modulated digital signal. I will not go into detail for GBus in this webinar because there will be a dedicated GBus webinar coming soon. The other two field instruments on this slide, the EDS 300 and the EDST 300, are able to analyze pulsed navigation signals radiated by ground installations like distance measurement equipment DME and tactical air navigation TACAN. Both devices have an RX and a TX part inside and test the ground stations by simulating a DME or a TACAN interrogator. The EDS offers an interrogation power up to 500 watts peak and is suitable for coverage measurements aboard of a flight inspection plane, whereas the EDST with 1 watt peak power can be used, for example, in a DME or TACAN shelter, or directly on the airfield. I would now like to give some practical examples for the everyday usage of the EVSG and the EVSF. It is important to understand that ground inspection and flight inspection are both in certain intervals mandatory for every landing system. Localizer runway measurements are typically performed by the respective air navigation service providers, ANSPs, with portable ILS receivers. For this, the receiver, in our case the EVSG 1000, is normally mounted in a measurement vehicle. One of the most important values to monitor by runway measurements is the difference of modulation depth, DDM, over the length of the runway. Each airport and each runway has its own fingerprint, and the ANSPs check whether the localizer's DDM curve containing the fly right, fly left information is within limits. Checking that, they can in the end verify if the runway still meets the ICAO requirements for its category. The same is done for the fly up, fly down signal, the glide path. For this, a mast measurement helps to verify that the glide is in tolerance and guides the pilot down to the runway in an angle of normally 3 degrees. The plot shows the DDM value over the flight angle. Flight inspection measurements require, besides the plane, more equipment, more time, and thus are much more expensive than ground measurements. Nevertheless, flight inspection is very important, as it is often the only way to check the signals in the air, right at the points in space where the approaching planes need it. There is a huge variety of different flight inspection measurements. As examples, I would like to mention here the localizer coverage measurement with characterization of the components of a 2-frequency ILS installation and an orbit measurement of a VOR station to ensure that the bearings of the radiated signal are correct in every direction. Last not least, I should mention that today drones and UAVs are increasingly being used by NSPs for measurement and characterization of NAV-8's ground equipment. This technology can be positioned somewhere in between ground measurement and flight inspection. It requires small, light, and nevertheless powerful receivers that meet the strong demands of the ICAO. Inspection with drones have advantages because drone measurements can be done at locations that are not reachable with traditional ground inspection and can be performed at much lower costs than conventional flight inspection. Concerning signal analysis, we have to differentiate between lab analyzers and field analyzers. Lab units are normally used for precision measurements, for example, reference measurements. Equipped with the option K15, the FSW offers high-precision ILS and VOR measurements. Time domain measurements, for example for detailed pulse shape analysis of DME and TACAN signals, can be done with different Rode-and-Schwarz oscilloscopes like the RTE 1000. Measurements in the field often require small and battery-powered handheld analyzers. With the spectrum analyzers FSH and FPH and the network analyzers ZVH and ZPH, Rode-and-Schwarz offers versatile solutions to do everyday maintenance on cables and antennas, like distance-to-fault measurements or vector voltmeter measurements, for example, to check phase and amplitude of the ILS localizer antenna elements. Last, but definitely not least in this overview, I would like to mention the different possibilities of signal generation of navigation signals. Rode-and-Schwarz offers with the SMA100B an analog high-precision signal generator that allows simulating ILS and VOR signals, for example, for a test of NAV-8 receivers in production or in service. The SMBV100B is a vector signal generator not only allowing to produce navigation signals like ILS, VOR, GBus or DME, It also gives you the possibility to play out complete satellite scenarios with a high variety of settings and configurations. In combination with power sensors, the SMPV100B can easily simulate a DME ground station, for example, to do DME interrogator tests in production or in service. As navigation and communication departments are often next door, the CMA-180 is a very compact combination of a communication tester for radio tests and additionally an ILS VOR signal simulator for navigation test purposes. I'm aware that such an overview can never be complete, and it lies in its character that it is not possible to go very much into detail and look at the different applications around the instruments. Therefore, please have a look at the family brochure All Doors in Flight and available application notes and cards around this topic on the Rohde & Schwarz webpage. As I said before, more webinars on NavAids coming soon. This concludes my overview, and I'm pleased to hand over to my colleague Paul.
Hello everyone, my name is Paul Denisowski and I'm a product management engineer with Rohde & Schwarz. In this portion of the presentation, we'll be discussing how the signals from different types of navigational aids are simulated using analog and vector signal generators. Navigational aids, or nav aids, are used for both en route navigation, that is, flying from place to place, as well as during approach and landing. The most common types of navigational aids in use today are VOR, or VHF omnidirectional range, the various components of ILS, or the Instrument Landing System, and distance measuring equipment, or DME. In addition to these traditional navigational aids, GNSS-related technologies are being increasingly used in all phases of flight. This includes the well-known global navigation satellite systems such as GPS, GLONASS, Galileo, etc., as well as regional space-based augmentation systems such as WAAS in North America or EGNOS in Europe. A newer addition to the family of GNSS-related technologies is GBAS, or Ground-Based Augmentation System. In this webinar, we'll be focusing on traditional navigational aids. The most common and flexible way of creating the signals generated by navigational aids is using a signal generator. In this presentation, we'll be showing the Rohde & Schwarz SMPV100B vector signal generator. Vector signal generators are general-purpose instruments that can create a very wide range of radio frequency signal types. In addition to the traditional navigational aid signals like VOR, ILS, DME, etc., vector signal generators like the SMPV can also generate different types of GNSS signals, and can even insert noise and interferes to simulate more realistic environments. Other modulation standards and even custom waveforms are also supported by general-purpose vector signal generators, and these types of instruments are suitable for both lab and field use. Let's examine how nav-aid signals can be defined and generated. We'll use ILS as an example. There are numerous important parameters that have to be configured when generating ILS signals. The first decision is which ILS signal component to simulate: localizer, glide slope, or marker beacon. Next comes the signal frequency, which can be expressed as an absolute number in megahertz or as a standard ICAO channel number. Clearly, we'll also need to specify the signal power. The core parameter of ILS glide slope and localizer signal generation is something called difference in depth of modulation. Here, the difference in measured modulation depth between two signal lobes is used by the receiver to align itself with a runway centerline or with a glide slope. And finally, the ability to configure a localizer COM ID or marker beacon type is important when testing the receiver's audio output. But beyond these basic parameters, there are a number of other important aspects when testing ILS receivers, or multi-mode receivers that use ILS as one of their inputs. Different types of frequency-related testing require both fine and rapid control over the generated frequency. ILS signals in the real world may change frequency due to drift or other errors. Since aircraft are in motion when they receive ILS signals, a non-negligible amount of Doppler shift may also be present on the received signal. This shift can be easily added when using a signal generator. In the case of ILS systems where both coarse and clearance signals are present, we need the flexibility of being able to set the frequency of our generators slightly above and slightly below the nominal ILS frequency. Equally important is the need to have both fine and rapid control over signal power. For example, the received ILS signal power will normally increase during approach. This may occur steadily as the field is reached, or it may be subject to rapid increases or fades due to terrain, etc. All of this can be precisely simulated and controlled when using a signal generator. Parameters such as automatic gain control and dynamic range are among the key performance criteria of a receiver, and testing these parameters also requires a wide range of input power. Noise and interference are facts of life in the real world, and receivers must be able to function properly in non-ideal RF environments. Vector signal generators often support the creation of AWGN, or additive white Gaussian noise, which can be added to the ILS signal. Constant or CW interferers are also used when quantifying the robustness of a receiver. An additional feature of signal generators is that they can create non-standard or impaired signals, which is useful for both receiver fault testing as well as during design, production, and manufacturing test. For example, we may want to change the standard ILS signal to remove one of the AM modulated lobes, or change the frequency of one or both lobes. Let's look at how ILS is configured on an SMBV100B vector signal generator. We first go to baseband and under avionics standards choose ILS from the list of available avionics standards. The next step is to choose which of the ILS components we wish to simulate. There are three components in ILS: glide slope, localizer, and marker beacons. In this example, we'll choose localizer. We can specify the frequency in two different ways. One is using ICAO channel numbers, such as 22Y. The other way is to use a user-defined frequency and specify carrier frequency in units of megahertz. After configuring type and frequency, the next step is to go to amplitude, which is where we'll configure difference in depth of modulation. By changing this value, we can control the amount of localizer needle deflection and in which direction the needle is being deflected, using either positive or negative values. We can also configure a COM ID signal. The COM ID signal can be enabled or disabled, and we can also define which Morse code characters are sent as the COM ID signal. Now that we've configured the ILS signal parameters, we enable the modulation. We can see that our frequency has been changed to the configured frequency, and we can also change the output level of the generator, after which we enable RF output. One additional capability in vector signal generators is the ability to add interferers or noise. This is done under AWGN. We enable this box and then choose if we want to add noise to our signal or add a CW interferer. We can also configure the parameters of this noise or interferer. For example, the ratio of carrier power to interferer power. We've discussed and shown how nav-aid signals can be generated by a vector signal generator. Vector signal generators provide the highest flexibility and the widest range of options in both the creation of nav-aid signals as well as things such as impairments, etc. Many of the traditional navigational aids, such as VOR, ILS, and ADF, are analog in nature, and this means that these nav-aid signals can also be generated using analog signal generators, such as the SMA100B shown here. The main reason for using an analog signal generator for these types of signals is that analog signal generators are usually significantly less expensive than vector signal generators. Although analog siggens do lack some of the more advanced features found in vector siggens, such as AWGN, they do tend to have higher spectral purity than vector signal generators. This is important if the same instrument is also used to generate high-quality signals for other types of tests. In terms of configurable parameters, however, both analog and vector signal generators provide very similar capabilities in terms of avionics signal generation. So in summary, it goes without saying that in order to test navigation receivers, we need a way to simulate the signals generated by a variety of different navigational aids. The signals should be controllable, reproducible, flexible, and efficient, both in terms of effort and cost. For these reasons, both analog and vector signal generators are the preferred method for creating most types of nav-aid signals. Vector signal generators have the highest flexibility and support for options such as additive white Gaussian noise, whereas analog signal generators can be used to create purely analog nav aid signals, usually at a lower cost, but also with higher spectral purity. And that concludes our section on simulating navigational aids.
Thank you, Paul. Thank you, Klaus. I would now like to wrap up today's webinar with an introduction to the future avionics testing webinars that are being planned in this series. Summarized in the top part of this slide is a simplified diagram depicting 4 categories of avionic technologies. Of course, each of these categories can be further detailed into many technology subcategories. Today's webinar has focused on our test and measurement solutions for air navigation. The full breadth and depth of Rohde & Schwarz's portfolio in aerospace and defense includes not only products and services in each of these avionic technology categories, but also extends beyond test and measurement. On the next slides, I shall provide you with a brief introduction to each of these planned webinars. First of all, a webinar in the area of high-speed aircraft bus testing, such as ARINC 429, MIL 1553, to mention but a few. This webinar will also provide insight into the Rohde & Schwarz solutions for industrial aircraft computer design and testing, which also enables system-level debugging by correlating measurements from different domains when troubleshooting a device under test. Following that, a webinar is planned on the topic of next-generation precision landing systems, namely the GBAS-SBAS landing systems depicted here. The certification of the GBAS Approach Service Type D, or GAST-D as it is known, for Category 3 landing procedures, will of course increase interest in the deployment of GBAS-SBAS landing systems. In this area, Rohde & Schwarz offers precision test solutions, not only for the design, but also for the test, calibration, and maintenance of GBAS, SBAS, and related technology platforms. The next topic, EMI/EMC testing. As mentioned before, it is a field in which Rohde & Schwarz is a market leader, with system solutions that can include the most advanced high-power amplifiers in the market. Depicted on the slide is a diagrammatic representation of a turnkey CSRS test system, or conducted and radiated susceptibility test system. And due to its modular design, it covers a wide range of test applications, which can be very easily adapted to different measurement tasks, but also for various markets, not only for military avionics. In this regard, EMI/EMC testing is of course a broad topic and stretches beyond avionic testing. And while such a webinar should have this broader focus, it will also include avionic testing applications. Finally, we are also planning a MILCOM testing webinar, and similar to EMC, this topic is broader than avionics testing per se. Such a webinar would also include ground-based MILCOM testing solutions, for example, RF and digital testing of air traffic control towers, such as the Rohde & Schwarz Voice over IP Mobile Air Traffic Control Tower depicted in the bottom left photograph on this slide. Last but not least, Rohde & Schwarz also have a dedicated team that develop and deliver customer-specific professional technology training, be it on-site or in a virtual classroom. If you have any requirements in this regard, please do not hesitate to contact us. With that, ladies and gentlemen, I would like to close off today's webinar with a slide and with the following message. We are in the process of developing an avionics testing competency guide, which will provide you with more detail on these competencies and applications. This you should be able to download from our website shortly. In the meantime, if you have any further questions or interest in the Rohde & Schwarz Avionic Test Solutions portfolio, please do not hesitate to contact us, either via your local Rohde & Schwarz sales office or directly at the following web address.